Thanks for the introduction. So yeah, I'm happy to present, or we are happy, Naman will present the second part. Our project, Adversarially Robust Clip Models, can induce better, robust perceptual metrics. And this project has been realized in collaboration with Francesco and Matthias. So we are looking at perceptual similarity metrics, which are basically functions that can take its input to images and then tell us how similar are these two images. And ideally, we would like that the similarity that is encoded by this function is similar to how humans perceive similarity, which in particular means that it should capture high-level semantics rather than just low-level structures. Such perceptual metrics can be building blocks for downstream systems. For example, later in the talk, we will see how it can be applied to content filtering. So early approaches towards similarity metrics were of algorithmical nature, and thereby they were not able to capture the high-level semantics, but just captured some low-level similarity. But nowadays, introduced by the famous LPIPS model, we can just use a pre-trained vision encoder, phi, and compute the similarity of the images in the feature space of this vision encoder. So in this case, we just take the cosine similarity, which means the inner product of the normalized features. And this vision encoder could be derived from, for example, a clip model or a dyno model, which are pre-trained, and you can use it in a zero-shot fashion. You don't have to train it for this task explicitly. And in order to measure or quantify the actual performance of these perceptual similarity metrics, we use two alternative forced choice tasks, which sounds complicated, but it's actually easy. And here we have the Knights dataset as an example. So we are given three images, one reference image and two query images. And the model has to decide which of the query images is more similar to the reference image. And this dataset is labeled by humans. So thereby we can quantify the alignment with human perception of some model. However, it has been shown that similarity metrics are vulnerable to adversarial attacks. For example, here we have these two dogs, and the metric says these two dogs are more similar to each other than this one dog to the image of a sewing machine, which of course makes sense. But then we can add some imperceptible noise to one of the dog images, and the decision actually flips. Now the metric says the dog is more similar to the sewing machine, which of course makes no sense at all to humans because we cannot actually perceive this imperceptible noise. So this could be a security risk, especially if such a model is used in a downstream system where it requires to be safe. So the goal in our project is to obtain an adversarially robust perceptual metric that also maintains high clean performance so that it's still usable in practical scenarios. And as a mitigation, we propose to use simply robust vision encoders for these perceptual metrics. And we have a work in last year's ICML where we show how one can obtain such robust vision encoders by fine-tuning existing pre-trained vision encoders. So this is called FAIR, and this FAIR loss basically measures the maximal deviation of the fine-tuned embedding of a perturbed input, which is the Z in this case, the deviation to the original embedding of a clean input. And so if we optimize this loss, we ensure that the embeddings remain stable under adversarial input perturbation. And so some experimental details, we fine-tune models on ImageNet, but using only the images because this method does not require any labels. And we use an infinity budget of 4/255, which is a standard value. As models, we consider a CLIP ConfNeXt-B model and a Dino VIT-B16 model. So let's look at some results. So here we have on the Knights dataset that I showed earlier, the clean accuracy on the x-axis and the robust accuracy on the y-axis. And we have some existing similarity metrics, so pre-trained CLIP and Dino models that are evaluated in a zero-shot fashion on this dataset, and we can see they attain kind of high clean accuracy, but they are completely non-robust. So the robustness is basically zero. Similar for the DreamSim metric, which is the current state of the art on this dataset, because it has been actually fine-tuned on this dataset. So it gets high accuracy, but still completely non-robust. Then there exists some prior work on robust perceptual metrics, RLPIPs, which sacrifices a lot of clean performance, and also the robustness is not very convincing. And LibSim maintains a bit better clean performance, but the robustness is also quite low, and actually this model is also fine-tuned on this dataset. In contrast, our robust models attain by far state-of-the-art robustness, and interestingly, their clean performance actually increases compared to their respective base models, even though they have also not been trained on this task, so they are still zero-shot. And this is something that we usually do not observe in adversarial robustness. So usually we have the case that we need to sacrifice clean performance in order to gain robustness. But in this case, it seems that robustness actually helps also for the clean performance. And with that, I'm happy to hand over to Naman.
Okay, thanks. So we've seen how these CLIP-like models can be used to measure perceptual similarity, and as a proof of concept, how it can be realized in an actual setting, we look at the case of content filtering. So CLIP is already used to filter datasets like Leon for NSFW, not safe for work stuff, and so on. So we create this experiment here where the goal is to have an automatic system that filters unsafe images from safe, right? So you can also do it for stuff like copyrighted, non-copyrighted, and basically you just need two classes. And the task here is that given a query image, we want to determine whether it is a safe image or an unsafe image, right? So we usually have these content filters. They have two retrieval pools, one for the safe, one for the unsafe, and you measure the average similarity of the query image to these pools, and then you assign the class to this image. And okay, yeah, like I said, CLIP is used for this task, and all other perceptual metrics can be used to filter content. And this is a safety critical task, right? So essentially, if you have a content filter, you don't really want any NSFW stuff or any weird stuff creeping into your downstream data set. So we want to make sure that the robustness here is actually, we make sure that we are robust in this case. And similar to the previous attacks, right, we again use the adversarial attacks here. So basically what we are trying to do here is, given a query image, we want to maximize the similarity of this image to a set of safe images. And for this set Y doesn't really need to come from this retrieval set that the content filter has. So the attacker doesn't assume any access to your retrieval pools. And you can just take, so in our case, we take 16 safe images that are randomly sampled from some data set, and you maximize the similarity of the query image under the adversarial perturbation to this to attain an adversarial image. And again, similar to the previous plot, for this case, this is a binary task, unsafe or safe. We have the infinity robustness on the y-axis and the clean accuracy on the x-axis. Again, the models that are completely non-robust but are commonly used as filters like CLIP and Dino, they attain very high clean performance but are more or less useless in terms of robustness. Models that are trained to be robust are slightly more robust, but they sacrifice a lot in terms of clean performance, right? Again, the baseline here would be 50% because we are dealing with a binary case. And in this case, if now we again apply our robust models, we see, right? So this is the ideal zone where we want to be more robust and more better in terms of clean performance. And for both Dino and CLIP, we see we are as good as the original model in terms of clean performance. There is a slight degradation in Dino, but we are much more robust. So essentially, you can use, ideally, you should be using these robust models for your content filtering, because you also don't lose anything in terms of clean performance, right? And this is also important because you also don't want a lot of your safe images to be unlabeled unsafe, right? That means your downstream data set won't have enough images from either class. And finally, we look at some interpretability stuff. So we want to ask the question, like, given our perceptual metrics, which images are considered similar by this metric? So this can be enabled by robust models, because robust models have better interpretable gradients. They're better aligned, and they can be used to, you can look at the gradient maps and stuff, and they look much better than their clean counterparts. So the task in this case is inverting an image. So given an input image X, or just given the embedding of this image for the vision encoder phi of X, we want to find an image X prime that maximizes this objective. So we want to find an image that maximizes this cosine similarity to the original image, right? And we are not even assuming access to X, we just need the embedding. And this X prime, so this is basically the adversarial problem. And this X prime, we start with the gray image, and we do just PGD, which is the projected gradient descent, even though I think we don't have any constraints here. The only constraint we have is that the resulting image should be a valid image. It's in the image box. So, okay, a trivial solution here is like X is X prime, right? But we don't assume access to X. So it's not unique, the solution. So we look for this optimization-based solution. And like I said, for clean models, we see here, given the original image, for the clean clip model, which is not adversarially robust, you don't see anything. You don't get anything. You can train it for, you can optimize it for as long as you want. All you get is noise. For the robust models, you retrieve semantically relevant features of the original image. Now, this is very nice because if you think about this phi of X, right? So this is basically an embedding vector of 600, 700 dimensions. Now from that, you can basically, without any tricks, just recreate these images, which are not the best in quality, but have very relevant semantic features. The same you can do, because we have a clip model where we also have a text encoder. You can do a cross-modal interpretability check. So given a text and the embedding of the text encoder, psi of t, I can see which image my joint model considers similar to the text embedding. And this can be used to extract concepts that the model has learned during pre-training. And this again is the same problem, but instead of the image-to-image cosine similarity, we have the cross-modal similarity here. Right? Again, we are maximizing for, we are looking for an image X that maximizes similarity while it's a valid image, it's in the image box. Okay, here are some examples. So for some well-known strings, like The Last Supper by Leonardo da Vinci, the non-robust model, basically you just get noise, but for the robust ones, you get some relevant features, right? So you see that there is a sort of a table and there's some people, hopefully people, the screen by Edvard Munch, and you see the face where you don't see the hands, but we see the face, right? So this is just by optimization. There's no augmentation, no tricks, nothing here. And so the quality of these images is a bit worse than the image-to-image one, because we hypothesize due to this modality gap that we have between text and image encoders. But yeah, without any fancy tricks, you can retrieve concepts that your model has learned, only enabled by our robust encoders. And to conclude, we show that the robust vision encoders that we have, they yield zero-shot perceptual metrics that have arch robustness, and they improve clean performance over the base models, can be used to enable robust content and dataset filtering, and have features that are interpretable in nature. So, thanks.